Mhm. Okay, now it is perfect. So, good evening to everyone. Sorry for the delay. We had some technical issues. And welcome to the second session of this seminar. Today we have the second part of Javi's talk about symplectic reduction and things of this sort. So Javi, whenever you want.
Oh, thank you. Thanks for coming again. Let us just resume a little bit what we did the last week. And I introduced what a symplectic form is, and I gave some examples. I said that on symplectic manifolds, the symplectic form locally looks always the same, in the sense that the Darboux theorem gives a canonical form that just depends on the dimension of the manifold. I told you, I proved more or less, I sketched the fact that symplectic manifolds are even dimensional, and I also said that there are certain topological constraints to describe, to ensure that a certain manifold is a symplectic one. I also gave you in this slide that there are certain sorts of manifolds which that meet canonically a certain symplectic form. I just recall that one of these manifolds is the cotangent bundle. Okay, I introduced the canonical structure of manifold in the cotangent bundle. I constructed certain coordinates out of certain coordinates of n of the variable of the manifold n. I constructed some new coordinates p1, pn that are usually called along with x1, xn adapted coordinates to the cotangent bundle. And by means of this, I said that these coordinates allow you to give a manifold structure on the cotangent bundle. Then I described how the cotangent manifold T star n admits a canonical symplectic form. I did it by means of the adapted coordinates. And firstly, I described the existence of a certain one form that is called a tautological differential one form on the cotangent bundle, okay, tau. And I commented that even if I use 13 adapted coordinates to define this theta, I commented on the fact that if you use another set of adapted coordinates, you will get exactly the same differential form. I mean that this differential form is independent of the set of adapted coordinates you use to define it. Indeed, I gave a second interpretation, a second manner, intrinsic manner of defining the tautological differential one form by saying that if you have a certain one form on the configuration space n, this can be understood as a certain mapping from the n to the cotangent manifold to n, okay? And so, as such, as since theta is a one form of this space, you can make the pullback, as done here, of the tautological differential one form on the cotangent manifold. And by doing so, you will get a one form here. And it turns out that the tautological differential one form is the only differential one form on the cotangent space manifold that allows you to say that the pullback of it gives you the differential form beta used to make the pullback. When we have this tautological differential one form, then we can construct the differential of it, and it turns out that the differential in adapted coordinates takes the form of the main example of symplectic forms. Indeed, this, as I said at the beginning, is the typical way of describing any symplectic form. Locally, by the Darboux theorem, looks like this, where these x, y, pi are called the Darboux coordinate, the coordinates that allow you to write omega as an expression of this sort. So it turns out that the cotangent manifold admits a symplectic form in a natural way, okay? And this was the last thing we were talking about last week. So now we are going to talk about Hamiltonian systems. So far, we have been studying symplectic manifolds. We have been talking about symplectic manifolds. And this by itself is interesting, but normally, and especially in physics, geometric mechanics, I mean, the part of mathematics devoted to study mechanical problems or physical problems related to mechanical problems. The main important thing is to study third-time short of differential equations. Indeed, we are mainly concerned symplectic geometry with differential equations of this form. Okay, you have a third-time manifold n. Okay, and for third-time manifold n in general, you can study a particular kind of system of differential equations. Okay, so you know this has dimension n. This is assumed. Yes, we are assuming that the dimension of the manifold is n. Okay, and we are studying this system of differential equations, where you see that on the left-hand side, you have the differential of the coordinates in terms of one parameter t, and on the right-hand side, you have that these derivatives can be written as a third-time function which depends just on the point of the manifold. Yeah. When you have a third-time system of first-order differential equations in this form, it is said that it's in normal form. Normal means that the derivatives of the variable here can be written as a third-time function of something that depends only on the variable on the point of the manifold. Okay, there are other sorts of differential equations where this cannot be ensured. For example, one example would be, for example, a differential equation of this sort. Yeah. In this case, you are not able to write the derivatives of the coordinates as a third-time function of the coordinates of the manifold here on R2, yeah, for example. Yes. So this system is not in normal form, and this system is in normal form. Anyhow, it's a matter of definition to say that once you have a third-time system in normal form of this way, you can, out of these coefficients, you can define a third-time vector field on the manifold in this manner. Yeah, it can be written, it can be proved, okay, that this has geometric sense. I mean that if you write this in all the set of coordinates on the manifold, and you write the vector field related to this in another set of coordinates, the vector field in that new set of coordinates is indeed the same as this in the old one. So you see, this is a well-defined geometric object. And once you have also a third-time system, a third-time vector field like this, okay, you can associate with it this system of differential equations. And geometrically, you know, if you don't know, I tell you now, that it is said that the solutions of these differential equations are called the integral cubes of x. And which are these integral cubes? They are curves on the space in such a way that at each point, this vector field is tangent to the curve. So the fun thing, the nice thing about this is that in many cases, when you are trying to study a certain system of differential equations like this, if you relate it to a vector field and you write the vector field you have a geometrical intuition to see what is going on to integral Q's. I mean, if you have this thing, this diagram, where we are representing this vector field, I mean, for every point, a vector field is just, let us say, intuitively, yeah, a third time, yes, vector attached to each point of the manifold is intuitively a vector field. More or less, seeing this vector field description, you can see more or less what cures are going to do, yeah, more or less. You can see that, maybe they can do this. And you can have intuitively, you can see, for example, that there are 13 trajectories to which the integral cures may converge, like here, yeah, more or less. Or there are certain solutions from which the solutions can diverge, okay, that can escape away from them. So this diagram is very interesting because more or less, okay, can you give you some intuitive information about the behavior of the integral Q's. And if you have a certain system of differential equation of this sort and you relate it to a certain vector field, drawing the vector field, you can more or less know what is going to happen with the solutions without needing to solve the system of differential equations. And normally, in many cases in physics, this is the main thing, that you don't exactly need to know what is going on to a particular solution. You sometimes want to know if they all get together, the central points, they get away one from each other, and things of the sort. Okay, this thing you have in here was something related to just vector fields and associated system of differential equations, okay? But it turns out that on symplectic manifolds, you can require the vector fields to satisfy an additional condition related to the symplectic structure. And this condition turns out to be very important to describe the solutions of the vector field. So the definition to take into account is the following one. We say that X is a Hamiltonian vector field, we mean on a certain symplectic manifold, if the contraction of the two form with the vector field is the differential of a certain function on the manifold, which is called the Hamiltonian function of the vector field. Okay. On the other way around, one can prove that given any function on the manifold, such a function will allow you to define only one Hamiltonian vector field. How this last part can be proved? Well, remember that omega is non-degenerate. That means that you have a third-time mapping from the tangents bundle to the tangents manifold to the cotangent manifold in such a way that given a tangent vector, you can contract the value of the two forms at the point at which is attached the tangent vector in such a way that you will obtain an expression like this. But remember, since this is bilinear and this is fixed, it will be linear in this, and it will be this. By putting a certain tangent vector in here, you will get a number. And the relation between this tangent vector and the result of applying this would be linear. So it turns out that this is an element of the cotangent manifold. Indeed, this belongs to the cotangent space at X of the manifold M. So remember that when the symplectic, when you have the omega and is not degenerate, this thing is a diffeomorphism. There is a relation 1-to-1. So it turns out that if you have a certain function, the differential of the function is something that for every point X gives you a covector, okay, belonging to the cotangent space at X. I mean, you can write this thing, yeah. So since this is a diffeomorphism, for every such a value, you will get something here whose image will match this, Okay, so you will always be able to find a certain element of the tangent manifold whose image contraction with the omega will be this. By means of the way of constructing, you can say that the image of a certain cotangent vector at x, it will be some tangent vector at x, because the way of getting it is by doing this, yeah, this contraction at x. So you can say that this element is the vector field at x. Repeating this for every x, you will get some way of attaching to every element of n a certain tangent vector, and this will give you the vector field you are looking for, the Hamiltonian vector field of the function f. So this is very important because it tells you that in symplectic geometry, for every function, you can obtain always a vector field, so-called Hamiltonian vector field. So the thing is that Hamiltonian vector field have many interesting properties, many interesting features, and it's very interesting to look for them, to analyze them. So the typical example, and one of the examples that really motivated the development of symplectic geometry and all this stuff, is classical mechanics. Indeed, this can be traced back to the 19th century, to the developments by Lagrange, Hamilton, and Poisson, who were studying the dynamics of celestial mechanics, of astronomical objects. Yeah. So the thing is that take the cotangent manifold with the canonical symplectic structure, okay? And so remember that the symplectic for locally can be written in this way. Yes, recall that these pi, xi are just adapted coordinates, and it turns out that omega can be written as in the Darboux theorem. So that's why we know that in the cotangent manifold, the symplectic form, the canonical symplectic form defined in the cotangent manifold is one in which Darboux coordinates, that adapted coordinates are Darboux coordinates, okay? The adapted coordinates give you some coordinates for which omega takes the canonical way. So as I said, it can be said that adapted coordinates are always Darboux coordinates. So imagine that you have certain function, and we have already said that every Hamiltonian function, every function will give rise to a certain vector field, Hamiltonian vector field, and let us try to look for it. So we can work out the differential, that it's easy, is the partial of the function with respect to each of the variables of the manifold, yeah? And the thing is that if you pick up the condition that the contraction of x height of the Hamiltonian vector field related to h will be the differential of h, it turns out that the Hamiltonian vector field takes this form. The interesting thing is that when you have this vector field and you look for the equations for the integral q's of this vector field, what you reach is that this must be the differential of the xi in terms of t, I mean this thing, and the differential of the pi in terms of time, it will match this. So what you obtain is the famous Hamilton equations of classical mechanics. So you see, the fun thing, the nice thing is that symplectic geometry allows you to describe in a very intrinsic and very elegant way that the equations for a Hamiltonian system are the integral q's of the Hamiltonian vector field related to a certain function. Now, one can try to understand more things to see what is going on apart from that. Yeah, and one of the things that one may ask for, may wonder what it happens with the change of a certain function along the integral q's of a certain Hamiltonian vector field. Okay, or you can understand that you have these differential equations that they are related with this vector field. Okay, and you wonder, imagine that this is your cotangent space. You are moving and you have certain function defined here. And do you wonder how this varies along solutions of your Hamiltonian system. So if you try to work out how it's going on, remember that along solutions, this will be that some function which depends on the coordinates and the moment, yeah, in time. So when you work out the differential in terms of time of this, you will take the partial derivatives of f in terms of the coordinates and the associated momenta, and the differential of these coordinates in terms of time. But due to the Hamilton equations, you will get that the differential of the coordinates in terms of time, the partial of h in terms of the pi, and the differential of the momenta in terms of time is minus the partial of h in terms of the coordinates. So this expression in here, it is called the Poisson bracket. And it is called the Poisson bracket because indeed it was Poisson who noticed that this bracket is important to describe problems in celestial mechanics. Indeed, it's interesting that it turned out that in several papers, Lagrange and Poisson, they were, how to explain it, they were chasing each other, they were competing among themselves to prove who could do the best result. They were trying, indeed, to use all these this now we know that they are geometric ideas to describe the equations of motion of asteroids, planets, and things of the sun. Another thing is that there are other brackets that were defined at that time. For example, they are the so-called Lagrange bracket. It was in 1808, 1810, and they were written in this way. B are two variables, okay? And they were written in this manner. So one student, and let us say that things of this sort, yeah. Wait a second. Well, in our notation is rather XR in terms of U, PR in terms of 3 minus PR in terms of U. Yeah, it is not B, it's inter B. It's a called Lagrange bracket. If you have never heard of it in your life, don't worry, it's the normal thing, because truly speaking, well, it turns out that they were not useful. I mean, they were used for a couple of things, but they were never again used. So yes, let me commend you that something that it can have interesting properties, because these brackets have certain interesting properties. For example, for describing symplectic folds, okay, it turned out that as time passes by, we notice that they are not useful for interesting things. So people stopped using them. And this is something that it happens in physics, in mathematics, and in research in general, that sometimes you can prove things that seem to be stupid, but since they are very useful, they become famous. And it happens the other way around. Yeah, that there are things that they are very difficult, but it turns out that they are not useful, and they are forgotten. Okay, so there are different options, and the level of difficulty of a theory sometimes has nothing to do with the fact that it becomes famous or not. Sometimes it's like a lot. Okay, so the thing is, as I told you before, we can say that for a symplectic manifold, we have reached the point that we know that there exists something called a Poisson bracket. So Poisson and other researchers try to understand the properties of this Poisson bracket, because they try to understand which are the characteristic properties of this bracket, okay, that at the beginning was linked to symplectic manifold. And after that, they noticed that this structure can be studied by itself, and it's not linked to a symplectic manifold. So little by little, okay? So recall, we have a symplectic manifold. It turns out that we have certain brackets, whatever it seems to be interesting. And this bracket can be understood as something that picks up two functions on the manifold, gives another function in the manifold. And the way of describing it geometrically is that the bracket of two functions is the contraction of the symplectic form with the Hamiltonian vector field of F and with the Hamiltonian vector field of G. Indeed, it can be written that this is the same as the Hamiltonian vector field of G applied to F. Okay, so this you can here see more or less how this this works. Yeah, when you have this differential function. So the thing is, once you have here such a thing, okay, turns out that this expression that it was for, well, the typical cotangent bundle, it turns out that every manifold locally has adapted double coordinates, and those double coordinates, okay, the bracket is written in this way. Yeah, so this is the characteristic form of the Poisson bracket. When you write this expression in double coordinates, you will reach to this thing. Everything in double coordinates is like in the cotangent bundle, locally in the cotangent bundle. Yeah, it's exactly the same. So you can see that this expression is bilinear, yeah, because it's linear with respect to F on the one hand, and it's linear also in with respect to H with the second function. Yeah, that's linear. It's antisymmetric. If you change the order F by H, H by F, this becomes the second one, and by changing F by H, H by F, this becomes this. So the plus term becomes the minus, and the minus the plus. So when you change the functions, it turns out that you obtain minus the previous result. So it turns out that this is bilinear or is antisymmetric, and it can be proved too that it satisfies the so-called Jacobi identity, that this is some kind of cyclic property where you see you have two functions, and when you have two functions, you pick up the bracket with a third one, and then you write exactly the same, but just by cyclically changing the positions. For example, when it's F, you write G, where is G, you write H, and where is H, you write F. And this one is obtained the same way. Where is H, you write the following one, H. When you have H, you write F, and when you have F, you write G. And when you sum up everything, it turns out that it's equal to 0. Yeah. And the other property that is interesting is that the bracket on each factor satisfies the Leibniz property. Yeah, I mean that F acting on the product of two functions J and H is the same as multiplying J by the action of F on H, bracket of F with H, plus the bracket of F with J multiplied by J. This reminds a little bit what it happens with a derivation, because indeed you have to notice that what this expression is telling you is that when you fix the first factor, this bracket acting on functions, it behaves like a derivation. That tells you indeed that this thing, okay, behaves like a vector field, because indeed, in this case, with the symplectic manifold, this is a vector field. Yeah, we proved previously, we said previously that this is minus the Hamiltonian vector field associated with the function F. Indeed, this property comes from the fact of this. Yeah. So one of the things you can prove is that when you pick up two functions and you obtain the bracket of these two functions, the Hamiltonian vector field of these two functions is the same as minus the commutator of the Hamiltonian vector fields of F and H. Okay, so the thing is that this is very useful for a number of reasons. And one of the things we have is that once we have the space of Hamiltonian vector fields with respect to symplectic for omega, you can prove the Hamiltonian vector fields are span a Lie algebra of vector fields. Why? Because you see, you pick up a certain vector field, Hamiltonian vector field, this XF, and you pick up another one, XJ. The Lie bracket of these two this minus can be written in here and this in here because this is linear with respect with the function. And it turns out that the Lie bracket of two vector fields, Hamiltonian vector fields, is again a 30 Hamiltonian vector field. So this space is closed with respect to the Lie bracket of vector fields. It can be proved also that the linear combination of Hamiltonian vector fields with certain constants is also Hamiltonian vector field, which makes this into a linear space and a so-called Lie algebra. Okay. So what you obtain now is that this is a Lie algebra. And the other thing you have to notice is that when you write this in coordinates, you obtain that a 13F, when you add the Hamiltonian vector field of F with it, what you obtain is that this is equal to 0 indeed. You can remember that this thing, by definition, what we said before, we have this, yeah, and we said that this is given by this, and this is P R is X R, that this is this, okay, sum equal 1 to n, yeah. And if you do this acting on F, what you will obtain is this. Which is obviously equal to 0. What means that when you have a 30 Hamiltonian vector field with a function f related to a function f, f is a constant of motion. So there are many of the results. For example, do you remember also that for a certain devolution of a 30 function f in terms of time, we wrote this previously, yeah, and it was this, and it was xh acting on f. So there is one thing, okay? Imagine that, well, if this is equal to 0, this means that f is an integral of motion, yeah? This means that this function does not vary along the integral curves of the xh. Yeah, it's something that is constant along solutions. But know that if you have two such functions, f, a, integrals, or constants of motions, they are called constants of motions on first integrals. There are several names. Motion of xh, yeah. That means that is equivalent to the fact that this is equal to 0 and this is equal to 0. But look, there is something interesting, because if you pick up this thing, this function, and you work out this thing, check out what is the value of the xh on it, you will see that by definition of a Hamiltonian function, a Hamiltonian vector field acting on a function, it will be this thing. Okay, you write the function and you put it at the end, and you write the Poisson bracket. And by the identity, by using the Jacobi identity, you could write this in this way, because we changed the order, yeah. And what you will obtain is this. That this is H acting on J. Wait. Second, this on JF. Yeah, acting on F and J. Okay, this will be this. By the Jacobi identity. Why is this way? Normally, because this is behaves like, well, it's the Jacobi identity. Yes, I want to, it's a matter of doing the calculations. So the thing is, this thing, the very important thing is that this thing, okay, can be written in this way. And we know that this is 0 because h is a constant of motion, so this is equal to 0. And this thing here, okay, is minus xh after f, which is equal to 0 because we said that f is a constant of motion, of the integral of the motion. So since this is equal to 0, this is equal to 0, the Poisson bracket of any function with 0 is equal to 0. See, this is to prove out of the expression of the Poisson bracket, and this is true. So it turns out that this thing is equal to 0 f h is a new constant of motion. So the Poisson bracket gives you a manner to describe new constant of motions out of known ones. And there are lots of results about how to use this to study Hamiltonian systems. But this is a very interesting result that is quite useful. Well, I will give you another example. Okay, so imagine that you have the torus on R3, get the surface of the surface of this donut. Okay, the differential equation, it has, well, the implicit way of writing is this one, and you can pick up locally 13 coordinates θ1, θ2. Okay, they are, you know, the angles along for a 13 circle. Okay, and there are also the angles of a circle this way with respect to a certain axis, yeah, something like this, and the second one is something like for a certain point, something like that. Yeah, so you can define the symplectic for the θ1, the θ2. You can say, yeah, but these coordinates are not well defined everywhere. How we say that this is right? Well, it can be proved that this is well defined everywhere. Yeah? Okay, θ1 and θ2 are not globally defined, but they can be constructed in such a way that the omega is well defined everywhere. So imagine that you have a certain Hamiltonian function of this sort, with omega is some value belonging to z, okay, something of this. So what you do, you pick up the differential of the h of this function, and you write the expression from the Hamiltonian vector field. You will obtain such a thing, something of this way. And when you have the Hamiltonian equations, you will get these differential equations. Okay, something of this sort. And if omega is like z, something like belongs to z, it turns out that the integrals are this way. Yeah. Now what you obtain it with something that is close. Indeed, why this happens? It happens because the Hamiltonian function here is well defined. Okay, and it gives you an integral of motion. As such, it turns out that when this is the integrals, okay, the solutions must be along surfaces where this function is a constant. So when you write out that you determine these sections, the motion of the system will be within these surfaces. So if you write this function on the torus and you see the spaces where it is constant, you will get a certain surfaces, or curves indeed, and solutions must be containing one of these curves. So it will be like this. It can be proved that if you have this system and omega does not belong to z, okay, you can obtain locally a constant of motion, but it will not be global. As it's not global, the motion is chaotic. Okay, it can be proved that it cannot be restricted to anything of this sort, and the cube does not close itself and starts to just going through the theories all the time. Okay, and there are lots of results about it, and it's very interesting because it can be proved that when you start, for example, for a certain point, you will never get the same point, but you will get as close to it as you want to. This is something of these sort of things. And there are lots of results about this behavior that it has, well, you know, it's interesting. If you think about, for example, the application of this in the celestial mechanics, you start with two asteroids and the motion between them, and it's no, there exists no this such integral of motion as we did with these Hamiltonian systems. Well, you will think that this asteroid with the second one will get not exactly at the same position, but as close as you want on each other. That means that sooner or later they will hit each other, because if they can be as close to between themselves as we want, and you remember asteroids are not ideal points, so they have some surface of some volume, yeah. So being too close means that they will hit each other. Indeed, one thing is that this is called symplectic geometry, that in certain problems like this with collisions, you have to generalize this because some singularities appear, and you will get to the so-called B-symplectic geometry, boundary symplectic geometry. It is nowadays very well. Is interesting, an interesting point, a field of research. So let me introduce now the so-called Lie group actions. Okay, and these Lie group actions play a fundamental role in the description of Hamiltonian systems and problems related to them. So what is a Lie group action? First of all, is a group action. I mean, you have a group, you have manifold on this case, and this thing is an action. That means that if you have the neutral element of the group, and it acts on every point of the manifold, leaving the point without motion, yeah, like it is. So it will be something like this. And the other thing is an action. That means that if you have two elements of the group acting, first G2 on X and then G1, this will be the same as multiplying the elements of the group acting on A, and they will be for everything belonging to the group. So there are certain definitions to remember. The isotropic group at a point X of the manifold is the set of elements of the group, leaving this point invariant. They don't move it. Okay. They are the orbits of the Lie group action, that is the set of points that can be reached by acting any element of the group of the point. Okay. Now, when you have certain Lie group, you have the so-called Lie algebra and the dual Lie algebra. And when you have a certain Lie group, you have the neutral element, and you have the tangent vectors to the neutral elements, and this is called the Lie algebra. Okay. Of the Lie group. And this is one of the important parts of the Lie group, yeah. And you have something called exponential. That is something that goes from the Lie algebra to the Lie group. Okay. So somehow, for an element of the Lie algebra, you obtain an element of the Lie group. Indeed, how this is done? It's done in the following way. I mean, when you have a certain element, let us say key, to keep the notation of this. When you have key, you can define so-called left invariant vector field on the manifold. That is a certain vector field whose integral cubes, when you multiply on the left by an element of the group, they're invariant. They can be invariant. They're the image of an integral cube of one of the vector fields will be another integral cube of it. Okay. So when you have these vector fields, left invariant vector fields, when you pick out this element and you fix a certain element of the Lie algebra, you will get a certain integral of motion, first integral of this vector field. And when the parameter of this integral reaches 1, you will get one element of the group. This is this, okay? So this is the integral curve of the left invariant vector field, such that the neutral element is key for the parameter t equal to 1. So the funny thing is that if you do that for every possible direction, initial direction, you will notice that you are able to recover every point on an open neighborhood of the neutral element. Okay, and that is why this exponential is called a local diffeomorphism close to the neutral element, because for every element of the Lie algebra, you will get an element on a neighborhood, open neighborhood of the neutral element, and there will be a relation 1-to-1 between them. Yeah, and my dears, this is the definition of the exponential. If you pick up certain groups, the matrix Lie groups, or certain Lie algebras, let's say, normally this is called GL. This is a matrix Lie algebra. There are matrices whose Lie bracket is the commutator of elements, and this is a certain Lie group of matrices. Okay. If you pick up this thing, what you obtain is that exponential of R is the sum 0 to infinite. I mean, when you have matrix Lie groups and matrix Lie algebras, the exponential is the expression you know. But for more general Lie groups, the expression for the exponential has nothing to do with that. Okay. Now, one thing that is important for us are fundamental vector fields related to a Lie group. And this, what is this? The formal expression is this one you have in here. But the idea is that when you pick up a 13 manifold n and you have a Lie group action on it, you pick up 30 points. Yeah, you pick up 13 elements of the group of the 4 exponential to key is an element of the Lie algebra, and you move x in one direction, and the tangent vector to this group is this fundamental vector field. This fundamental vector field have interesting properties. Okay, they close an algebra, and they are related to lots of problems, and indeed they are used to describe symmetries of physical theories. So they are very interesting. Yeah, and they used to be used to study many physical problems. So let me explain you a couple of things. We finished live, so I will speak for some 5-10 minutes more. Yeah, and I will finish, and I think that we left still the last part of the talk, the reduction, Marsden-Weinstein reduction for the third time, of the talk. Okay, to extend it for a week, and I will finish with this soft introduction to symplectic geometry, the basic of symplectic geometry. Just let me describe a couple of actions and a couple of things. And let me tell you that in the same way as the cotangent manifold has a certain canonical structure, and mathematicians and mathematical physicists will love having canonical things on the spaces. It turns out that given a Lie group, we have 13 actions that can be defined in a canonical way. And not only the groups, but the Lie algebras and the dual to them, they have also certain canonical structures. And it turns out that for some reason, used to happen in mathematics and physics, that these canonical structures, when they are beautiful, they have nice properties, they used to be useful. So the things that when you have a 13 group, you can define a 13 axiom of the group on itself on the right. What does it mean? That given a pair of elements G and G, we have 13 action on the G, on the manifold G on the Lie group. And how it is done? Given a pair of elements G and H, the action of G on H is just multiply by J on the right side by -1. It can be proved that this thing is a certain action of G acting on G. There are another action of G acting on G on the left. And it's called on the left because if you have 13 elements G and H, okay, here the Lie group G is acting on G, and for every element H of G, the action of an element G on the group is just to multiply G and H on the left. Again, it can be proved that this is an action, okay, is the action by left translations. So you have 2 canonical actions defined on any Lie group, and there is a third one. And the third one is the one by so-called internal automorphism. And in this case, it's again an action of the group on itself. And when you're given J, the action of J on element H of the group is nothing but multiplying on the left by J, multiplying on the right by J minus 1. You see, it's something similar to what we did, something that it is a mixture of the previous one, and it just sets that EJ is nothing by left J, right J minus 1. Well, this is normally written to be J acting indeed on H, and this is the multiplication left on H. So once you have this is, as I told you, is the action of G on itself by means of inner automorphism. And the thing is that you can do now, you can define now two Lie group actions on the tangent space to the neutral element of the group Lie group, this is called Lie algebra, and the dual one. And it turns out that by doing this expression, this is called the adjoint action, and this is called the coadjoint action. There are two natural ways of acting by a group on the Lie group, on the Lie algebra of the Lie group, and on the dual to the Lie algebra of the Lie group. Again, both things, they have lots and lots of applications. So now let me give you some example of these things. For example, assume that you have a certain Lie group, R3. R3 is an abelian group with respect to the sum. Yeah. So it turns out that if you pick up elements of the Lie group R3 and you pick up the neutral element, I mean 0, the 0 vector, if you try to work out the Lie algebra, it will be the set of tangent vectors to q's passing from the 0. Yeah. So, you know, it's evident that given these cubes, every cube will give you a certain vector field on R3. Yeah, because you have R3, you have the 0 for every cube passing through 0. This cube for sure does not pass through 0, something like this or this or this. You will have all possible vector fields attached to 0 in every direction. So the Lie algebra to R3 is just R3, because these are all vector field tangents to these cubes. They give you every possible direction, and every possible direction is a tangent vector to a certain cube passing right. I mean, it's easy to notice that. Yeah. So the action by inner automorphisms is stupid because, you know, given a certain element of R3S and R, you have to act R on the left, I mean to sum R, and then on the right by minus. But you see, this is abelian, so it's just the identity. Every element of R3 acts on R3 as the identity. It has no much sense. Well, the much sense is trivial, let us say it this way. And when you pick up the adjoint action, it turns out that it gives you the identity, and the coadjoint action gives you the identity too. So the following thing, and the last thing I will describe today in detail, is the lift of Lie group actions. And the lift means that when you have an action of G on a manifold, you can define new Lie group action of G on the cotangent bundle, and it can be done this way. So the thing is that, I will just describe what is going to be next week. The thing is that in these things, in physics, it turns out that the typical space in Hamiltonian mechanics is a cotangent bundle. The configuration variables, the variable of n, give you certain adapted coordinates on the cotangent manifold. This will be the p's and the q's or x on the original one. The p are called the associated momenta. And it turns out that when you have a certain system and it has symmetries of a certain kind, there are symmetries which leave the symplectic form invariant. That it's used to happen in physics. It turns out that these symmetries, okay, they are such that they allow you to ensure that if a certain Hamiltonian function is invariant with respect to the Lie group action, you can construct constant of motion by means of it. Yeah. In physics, when you have certain Hamiltonian function and you have certain symmetry of the Hamiltonian function that leaves the symplectic form invariant, you have the so-called net theorem, which tells you that certain Lie group is related to certain constant of motion. This constant of motion, mathematically, they are gathered, okay, and they are momenta in classical mechanics, and they are gathered with a certain map called the momentum map. And this momentum map has interesting properties, and it allows you to describe symmetries of systems, and it allows you to simplify systems. Indeed, it turned out that in physics, when you had certain symmetries, and these symmetries gave you the invariance of certain momenta, physicists notice that there are certain chains of variables that allow you to simplify the initial problem on a Hamiltonian setting, transform it into a new problem also in a Hamiltonian setting. Means that with coordinates, configuration coordinates, and moment, sensitive moment. It turned out that mathematically there is a well-known procedure, or now well-known procedure, called the Marsden-Weinstein reduction, which describes how to do it. So what the physicists were doing intuitively, it can be formally done by means of this theorem. And you don't have to imagine how to do this reduction. The theorem tells you how to do it. So I think that I will finish here. I hope that this was interesting. Thank you very much for attending. Well, that's all for today.
Okay, thank you, Javi. Are there any questions or comments? No, there are no questions or comments. I have a comment, Javi. Could you, I think it would be interesting if you could write the intrinsic definition of the canonical one form in the cotangent bundle. Maybe this way they will understand why is it canonical. Actually.
I mean, it was written. I will.
I mean the intrinsic as the transpose of the tangent of the projection of the cotangent bundle.
I mean, second. I mean,
you know which diagram I'm talking about, right?
Wait. Now I'm not sure what are you talking about, really.
Okay, then write horizontally the projection of the cotangent bundle, but as an application. I mean, in horizontal.
I don't know what you mean now.
Yeah,
wait.
T star n,
yeah.
arrow n. T star, okay, arrow n. Okay, now write the cotangent map associated to this.
The thing
you can write it upstairs. I mean,
the thing is that what you can write it. Now I know what you mean. That's well, this form, the canonical form, it can be write it, because the nicest way to write it is intrinsically is what I said before, the way what is canonical. But anyhow, this is a form of the cotangent. So for every point xp, this is an application from the tangent space to the cotangent bundle.
Yeah, that's right. To R.
This is the thing you are doing. This is the canonical form. The canonical one form. So it means that it goes from the tangent to the manifold what is defined to R. For at each point. So when you have something of this, you have a certain tangent vector.
Exactly.
At this point. So when you do such a thing, this can be
the only thing you can do, actually.
It's the only thing. Well, the thing is that when you have such a thing, what you can do is just, you have a certain thing. When you have this tangent space, you have this. This is the projection onto n. So once you have the projection, you have something that goes from the tangent to the tangent, cotangent to the tangent. So here you have x pi, and here, well, you know, you have the projection, it will be to the tangent space to x, yeah?
Maybe you should
Because
write the transpose of this.
here to x. You can, no, it's, I mean, wait a second, because there are several ways of doing this. So when you do this, normally what it's written is this thing.
Mm-hmm. Yeah, exactly. Exactly.
I mean, this is the way of
Yes.
writing it, but you can, as Xavi said,
transpose, yes.
you can write the transpose of it, because this thing, yeah, this well, this is the tangent. Well, this is the tangent to P at the point XP, yeah? So you can transpose this mapping, and by transposing this mapping, it goes from here to here. This is the transpose to here, yeah? Because you put the dual on the dual. So if you use this, you can write it this way.
Yeah, exactly.
This is the other way you can write it down. So it turns out that by using this, you can write this thing. That's theta xp. You don't need to write this because in here, yeah. So the only thing you have to write is
exactly.
This. Okay.
Exactly, and this way you can say that you just need the canonical projection to define it, so it's
to define yes, the canonical one for. But indeed, is what is this expression is what you saying by doing this.
Yeah, exactly.
Because they are exactly the same. Okay. The thing is that imagine that you have this one form, so it's something of this.
Yeah, but maybe this way you say is the only form satisfying this, but maybe why does it have to exist one
yeah
form?
The thing is that you can imagine that when you have this form, it can be written this way. Yeah, this one form, this is a one form on a manifold n, so you can always write it this way. So, and on the other hand, you have this thing in here, I mean this the pullback, yeah, and you have remind that beta can be understood as something like goes to here, but for every point of x, it gives you x and now one covector, something like is that something like this. You can write it, yeah, beta e.
Yes.
So the coordinates, this can be written as the coordinates and these coordinates. This is how it goes. Yeah. Well, this is that the PIs and this is the coordinates quite the thing. So when you pick up the pullback in here, what you will get is this a function and things of this sort, and you will have this bi of this thing. But you notice that this must be beta I dxi. So that means that here, what is here must be equal to this, and this must be equal to 0, whatever the beta is. So that means that beta e must be equal to 0, because you want to delay this. And now these functions must be the beta I. But this means that you have to pick up, yes, the moment, yeah, pi. So RE must be pi, because then when you do this, it's the thing that gives you beta. So what it turns out is that must be something of this sort. So, you know, by writing this condition on coordinates, you will get this. That is the only thing that works. And this will be always the same no matter where the adapted coordinates would be. If you write this thing this way, you will get, I mean, by using this, you will write that this condition, and these are different ways of writing exactly the same thing. They are absolutely equivalent. So this is the other way of describing the canonical one form in an intrinsic let us say this half intrinsic manner. At least, I mean, this is intrinsic, yeah, this thing. You here, well, intrinsic. The thing is that here you have canonical coordinates, yeah, to define this. So when you are using points, so it's not exactly in terms of coordinates, but when you describe this you have this canonical description. It's not absolutely coordinate free. It's something on in between. So let us say that this thing is intrinsic. We can say that this thing is half intrinsic.
Yeah.
And this thing is in coordinates, yeah.
Yeah, exactly.
So there are three manners of describing this.
Well, I hope this helped understand everyone.
Well, truly speaking, there are more manners, okay, of describing it, because the symplectic form and the tautological form, they have certain properties with respect to the symplectic structures, and there are funny things between them. I mean, there is one thing, there's something called the Euler vector field of the cotangent bundle, and it turns out that you have something of the sort. Okay, once given this gives you the one form, and there are 13 relations that can be used to describe these things in the same manner. Well, there are different things that can be done, but yeah, this is the expression. So I hope this answers your question. So any other question?
It was not a question, it was more of like a comment, but okay.
Yeah, a question, yeah, a comment, yeah. Anything else?
Does anyone else have any question or comment? Javi, what happens to them? I mean, are they shy or are they afraid?
Maybe they are shy.
What's going on?
Or they haven't understood. I didn't explain this properly, maybe. I expect no. Anyhow, I would tell you that this is easy, but things about symplectic geometry, they are very, let us say, fancy. There are a lot of things that can be studied and things that can be done. For example, what I told about integral of motion, people are crazy about doing problems where you have a certain problem and you have certain integral of motions, J, and they satisfy this relation. I mean, you have this. You have Hamiltonian system, and it turns out that it's equal to 0 and things. When you have enough such things, when you have that the dimension of the manifold is 2n, and you have one and it turns out that they are functionally independent, they said that this is an integrable system. And this has been studied for many years, and they are very interesting. This system, they are very interesting. They are classified as the problems given by Perelomov, for example, and others. Winterneath, and so on. There are lots of words about it, but it turns out that there are 30 systems in which it may happen that this thing, they are not commutative. They are 13, and this is a Lie algebra. And this is called non-abelian integrability. And this is something that is studied now. This problem, when you have this problem, it's very interesting because when you start studying these things, it turns out that the dynamic of the system can be described by means of 13 torus. Yeah, I mean, the phase space locally is something like this, and there are certain invariant toruses where motion is around these toruses. They do such things, they're moving around this. Yeah. Then normally when you write certain spaces of phases, for example, T star R, well, there appears something, well, not torus. So when you have T star, these are just some kind of circles. They are not exactly circles. They are things like they are homotopic to circles, okay? Some things of the sort. But when you have this, and you have a certain manifold, the structure of the cotangent space, this space is where the motion is constrained to, they look very much more involved. Anyhow, they still have certain properties that allow you to tell how the system is behaving, and they are nice, okay? That you can restrict them. There are certain structure that appear, okay? But they are still nice, okay? On the contrary, they are chaotic systems where, well, you know, you start by a point and anything can happen in reality. For example, like in the torus, yeah, that you start at a point, you start then turning around, and going back to the first place and doing the same again without turning up to the initial point. So let us say that in chaotic systems, in a certain sense, you don't know what is going to happen. In integrable system, the things that can happen are very specified. They are very, let's say, rigid. And then there are these things that they are richer. And they are also very interesting. So there are lots of works on it, and there are lots of interest in studying these things. And in astronomical systems, celestial mechanics, well, there are lots and lots of works about it. It seems that classical mechanics, people used to say that classical mechanics is that. I mean, that everything that was interesting was done, and what is important is field theories and things like that. And it turns out that in mechanics, there are still many interesting problems to be solved. And astronomy, well, you know, it's just, there are many open problems, and they are very interesting. Okay.
Now I have a question, Javi. Now
Yeah.
I have a question. But are you saying that integrable systems cannot be chaotic?
They are absolutely contrary to chaos.
But for instance, the double pendulum, it is not integrable? Because the simple pendulum is integrable for sure.
I mean, yeah, I think that is chaotic, I guess.
The double pendulum is chaotic for sure. But,
yeah.
I mean, is it integrable?
No.
I think it might be non-integrable because there is a non-holonomic constraint on the velocity. That's
yeah, you're right.
It cannot be integrable. Chaotic means normally that the evolution can, for example, in the chaos, in these things, you will have something of this sort. Yeah. When you have integrability, yeah, you have certain constant of motions. Normally, in this case, it's a 4-dimensional one. You will have 2. Yeah. And when you have such a thing, immediately what it happens is that these 2 integrals of motion allow you in this 4-dimensional manifold to cut everything on a torus. Yeah, 30 toruses that are by means of these 2 functions. So this is what is called an integral system. On each one of these toruses, it can be whatever. Yeah, it can be some things like that. Now, normally, you know, when you have integrability, what it's going to happen is that your motion is more and more restricted. It's more packed in a certain place. You cannot say that from every point to another point, anything can happen. Yeah, within one of these toruses can happen whatever. You don't need any restriction. But you know, normally your motion is very restricted. To say what is exactly house, yeah, the thing is you have to give an exact definition of what you by house mean, yeah. And depending on how you want to define it or what you to expect, it can be that integral system can be chaotic in a certain manner. But the idea that from initial condition, the final condition can be someone else, because chaos is about initial conditions. It's about normally about the fact that when you change a little bit the initial conditions of a problem, the evolution can drive your system very far away from the initial condition, yeah, that you can generate absolutely different things. This is chaos in reality, in intuitivity. But if you have restricted your problems to 13 thoruses, you are saying that your problem is not going to any other place, and the difference between the solutions will be somehow bounded. So it's not a typical chaos as such. There are systems that they are called super integrable indeed, in fact, and these systems, even in this case, they will be a third one constant of motion. Yeah, and if you have such a thing, it turns out that within the torus, you will be again to the initial problem. I mean, we have something, and it will be close with it within this torus. So, as you say, chaos can be understood as something contrary to integrability, because chaos is about going to everywhere, not knowing what is going to happen about the evolution of a system, at least intuitively. And when you have integrable systems, but you have so many integrals of motion that your motion is restricting and restricting and restricting and restricted to this problem. Yeah. At the very end, you will have some manifold, and your problem will be restricted to this manifold. What is going to happen on this manifold? Well, you know, it depends on the number of things you will have. And in this case, with two integrals of motion, we have a, you know, a two-dimensional manifold. Locally, under certain conditions, okay, if the system is integrable, you have action, how it was called?
Action angle.
Action angle, yeah, I'm a little bit tired already. So the thing is that the evolution would be something like the differential of the Fi, because these are used like coordinates equal to 0, and for every I will be one coordinate, and the will some function will depend on F1, F2, something of the sort. Yeah. 0.
The Liouville-Arnold theorem.
Yeah. And you will have something of this sort. So you see, this θ1 and θ2, they don't need to be related some, because you have certain functions here. I think this can be whatever, yeah. So like in the torus, they can be restricting or restricted, whatever. But you know, when you have these two constant of motions, yeah, it's considered as momenta, and it turns out that you have two functions that they are here two constants. But depending on the nature of these constants, there's two, the motion within a torus will be or without a submanifold or doing weird things. So what does chaos means in this case? I hope you pick up the point. Here, you have to be very careful about your definitions to say what is chaos, what is integrability, yeah? But the idea is integrability means restriction of the possibilities, how chaos means that your system can behave in a wild way doing whatever. When there are integrals of motions in action, you have restrictions and your system starts behaving like a good guy. Yeah.
Yeah. Okay, so thank you. Javi, are there any more questions or comments? No? Okay, then let me say that next week we are not having this seminar because it's holidays. So we will meet again on the 13th of April at
And I will finish the talk.
Same time. Yeah, and Javi will finish or not. We'll see. Yes,
I hope so. One question.
Hopefully, Javi will finish with the reduction, but if he doesn't, we will have a fourth session. So don't worry.
If you want to. Anyhow, if you want someday to have any topic, you can propose it. You can send to Xavi, and one of us can prepare it. If you have any question or any comment or whatever, we will be very. It will be a pleasure to answer and to prepare something for you.
Or if you want to give a talk.
Or you want to give a talk too.
Or if you want to give a talk, you can also ask for it.
There are many topics. I know that some of you would like, for example, supergeometry. I could do something like super mechanics for dummies. I mean, an introduction, some soft introduction to super mechanics or whatever. So you only have to ask.
Okay.
Thank you.
So thank you all, and see you in a couple of weeks. Have a nice holiday and see you soon.
See ya.
Thank you very much. See you.